Mike starts his run 2.5 kilometers south of the Art Museum and runs north for 30 minutes at 9 kilometers per hour. Where does he finish? Well, like any problem, let's start with drawing a picture. Make sure we understand what is going on in this problem. So I'm going to draw the Art Museum. We'll just draw a little house, a little building here. All right, it's got some windows. All right, picture's not that important. What is important is some orientation. So I'm going to make sure we're all on the same page here. If I'm looking at a compass, there's east, there's south, west, and north. So we're going to agree that going up on the page is north, which means if that's the Art Museum, Mike is south of the Art Museum. He's down here, and he's running in that direction, right? And how far south? Well, he is 2.5 kilometers away from the Art Museum. And he's running with a speed of 9 kilometers per hour. And the time of his run is 30 minutes, right? So I've kind of organized all my work here, and you might get a general idea where he might finish. If he was to go for 1 hour, he would go 9 kilometers. So intuitively you might think, well, let's say he's going to go 4.5 kilometers. I think that's going to put him on the other side of the Art Museum. So I'm just going to estimate where I think he's going to finish. Right, there's his finish line. And since they say of the Art Museum, let's give an answer relative to the Art Museum. Right, so if this is the Art Museum, well, what is this distance from here to here? That's ultimately what I want to know, right, is where is he relative to the Art Museum? So where do we go from here? Well, one of the best ways to organize these is to think of this as him running along a tape measure, right? If this is my tape measure, let's say we got to define where 0 is. Well, if we want to know how far he is from the Art Museum, it might make sense to call this a location of 0 kilometers at the Art Museum, which puts him south of the Art Museum, and let's call south negative, so he is located at negative 2.5 kilometers, which means he's going to finish somewhere which we want to know. This is going to be our final position, right? So when we set up these problems, this is an object moving at constant speed or constant velocity. We have a couple equations for objects moving at constant speed. We have speed is equal to distance over time, and we have velocity is equal to displacement over time. The velocity equation is more powerful because it allows us to really account for the direction, particularly here when we're running north and south. And this same equation can be rewritten as v is equal to the change in position, x final minus x initial, over time. And this itself can be rewritten as a linear equation of the final position is the initial velocity times time plus the initial position. And as we learn in position time graphs, where we're located, x, is a function of the velocity, the slope, times the time, plus where we start. And if I wanted to graph this, I could graph this problem. And you would have the Art Museum here at the origin. This would be position, this would be time, and he would be located down here at negative 2.5, and there would be some kind of positive slope. He would be going up 9 kilometers every hour. Let's call this 1 hour. And he's going to go up about 9 kilometers. He's going to be located right around here after an hour. And you might see a slope here, and that slope would be his velocity. The slope is 9 kilometers per hour. And what we want to know is, well, where is he at the 30-minute mark? Half an hour, right? And he's going to be located somewhere around here, right, which looks like it is, there's north, there's south, a little bit north of the Art Museum, right? So this is kind of the general idea here. But ultimately what we really need to know is all these pieces of the puzzle. So let's write our variables. All right, let's start with the variables in our equation. We have a velocity. He is moving north. Let's call that positive 9 kilometers per hour. There is a time at which he's traveling. He is traveling for 30 minutes. Now be careful. When we write units, you might see that we have minutes and we have hours. And in our equation, we're going to be multiplying velocity and time. So let's convert one of these to make sure we're speaking the same language. So I'm going to take my time and I'm going to convert the time right here to hours. By using a fence post, I could put minutes in the denominator, hours in the numerator. 1 hour is 60 minutes. When I do that, minutes cancel, and I get my time is actually 0.5 hours, which hopefully you didn't need a fence post to do that, but we now are speaking the same language, right? The times are all in the same language. We're in hours. And here we can look at a couple ways to put this. You can use delta x, and we're trying to solve for delta x. That is what we don't know. If I know my displacement, I can answer my question later. Well, let's use it this way. Well, we know that v is equal to delta x over time. And therefore, if I want to multiply both sides by t, I can find that delta x is just simply equal to velocity times time. And I know both of those values. Velocity is 9 kilometers per hour, and my time is 0.5 hours. Notice my units, my hours cancel. I get a displacement. Delta x is equal to positive 4.5 kilometers, right? Which means he's going to be displaced 4.5 kilometers, which is going to put him, well, if he goes 2.5 back to the art museum, he's going to have an additional 2 kilometers to go, right? So if that's the case, I know that he's going to have 2 kilometers. He's going to be north of the art museum. So that's one way to do it. That's actually going to be our answer in this problem. But let's look at how we might use this other variation of our equation to make that answer a little bit easier. Rather than doing delta x, what if we write x initial and x final? And we know x initial. X initial is negative 2.5 kilometers. Remember, he's south of the art museum. South was called negative. And he's going to finish somewhere. And if we take all these variables and we use this version of our equation, x final is vt plus x initial, then we can plug in what we have. Our final position, which is what we want to know, is equal, again, to 9 kilometers per hour times 0.5 hours, plus my starting position, which is negative 2.5. And when we do that, you'll see that you get 4.5, the same 4.5 kilometers, but now you're going to be subtracting the 2.5 kilometers, and you get a final position of positive 2 kilometers, right? And there we go. What does positive mean? Positive means north. So we get back to our answer, 2 kilometers north of the art museum. All right, so a couple different ways. Again, if you draw the picture, we can get to that answer either way. And we're going to find that this variation of our equation is really useful, right? It not only allows us to find these positions and interpret it the way we did in the second part, but you also see that this is our slope-intercept form of our position function, right? But remember, we're dealing with position and time, so we have, instead of y and x, we have x and t, right? So again, this model for constant velocity is going to be a very useful one here moving forward as we solve problems.